Okay. Yeah, the last trilogy is, yes, honestly, the last three, they killed it. They killed the Star Wars universe. I hate you, Disney. Like you really, you really suck. You know, I mean, the seven, it could have developed, but then eight happened, and then it's like, okay, oh my God. And nine was, God. Okay, I gotta watch that. I got Mandalorian. I heard good things about it. I gotta get that Disney Plus and get after it.
Yeah, the new episode came out today.
All right,
It's
cool.
really good.
Yeah, I probably gotta binge watch that. Okay, so we're 0-0. And then the first second, let's say we went 5 meters in the first second, then dramatic increase, 5 to 18, not to 10 anymore, not to 15, 18 to 39, 3 seconds, 67, even more so, even more dramatic. We went from 21 to 28 there. Dramatic increases. And at least The Mandalorian is really good. Also, Clone Wars series is good. I heard about Clone Wars, 7 seasons. Clone Wars, this is the animation. Yeah, it has to be the animation. So, yeah, we'll see about that in my vacation time. Yes, thank you, Sophia. It's the animation. Yeah, they have a good series. Okay, so dramatic increases every second, 67 to 120. Okay, you know by now that the gaps are, motion map, get increasing. Non-linear data. The gaps, that means that the gaps are dramatically increasing or gaps are not equal. We know that already, because if the gaps are equal, we have constant velocity. If the gaps are increasing or decreasing, doesn't matter. Dramatic, for effect. That's an acceleration or deceleration. When they're increasing, that's accelerating, that's speeding up. When they are decreasing, slowing down. You're going from 65 miles an hour, you put on the brakes and these gaps start to get slower and slower because now you're not moving as fast. So things are creeping along every second. Now for nonlinear data, we have best fit curves, not best fit lines. So when we plotted all that data, what did we get? If we scaled it right, you could actually see this quadratic function going on. We have this best fit curve, a curve of best fit, a curve that best fits all of the points. And then we started talking about these slopes here, but we'll come back to that. We also define the slope. The slope of a position time graph is the velocity. And therefore also the slope of a velocity time graph is the acceleration. I think we get to that next. For nonlinear data, there are many slopes, okay? So for nonlinear data, we have several slopes, but as we saw up above in the other example for constant velocity, there's only one slope. These notes from back here, October 26th. Only one slope for constant velocity. You can have the same, like if you take these 2 points, it's going to be the same slope as this point way out here and 0. It's the same slope for all of these points. Same. The gaps are the same. The slope is the same. This is a constant rate of change, a constant position change. It's equal. The gaps are equal every second. When the gaps are equal every second, that's a constant slope, which means a constant velocity. And if we were to graph this constant velocity, which we have done, we have xt here. If we have vt here, the slope would look like, or the line would look like that, to say that every second you have the same velocity, constant, 5 meters per second, 5 meters per second, 5 meters per second to infinity. All right, so it's the same slope. The slope of a position time graph is the velocity. So every time we take this slope here for any 2 points, it's going to be the same everywhere. You're going to get the same value. Same slope, same velocity. Constant slope, constant velocity. Right? Remember that? I hope you do. Any questions? Because when, again, not to even say this enough, I can't say it enough. You have to identify what data you're looking at. You're looking at position versus time. Okay. And if the data is linear, you're going to have a best fit line. If it's linear, it's a line of best fit. That's going to go through all of your points. This guy's hanging out. Who cares? You try to fit all the points. Because in reality, maybe based on your experiment, you can have a line up here, line down there, line up here, but you know that the data is linear, so you're going to draw a line. You're not going to guess. There's no guesswork. As we stated, for linear data, the slope will be constant. Therefore, the velocity is constant by definition, right? Because we have established this. This is what we know, and therefore we can interpret this accurately. For linear data, the slope will be constant. Therefore, the velocity is constant, and there is only one slope for linear data. These notes are important. Constant velocity. There's our constant linear data stuff. Gaps are the same for every second. Motion map depicts the same thing. Gaps are the same for every, position for every second. First second, second, 2, 3, 4, 5. And then we come here. The car speeding up, increasing position in the east only. So we have the gaps are going to dramatically increase. 518 is growing. We're speeding up, getting faster. Need for speed, 0 to 60 miles per hour in 10 seconds or 6 seconds or whatever. Gaps are increasing. Nonlinear data, best fit curve. The gaps are dramatically increasing or gaps are not equal. We have best fit curve now because the gaps are increasing. Okay, again, we are still looking at a position time graph. It's just different because the gaps are increasing. We have a curve. Let's see. Yep, so same definition. The slope of a position time graph is the velocity for nonlinear data. Unlike linear, for nonlinear data, there are many slopes. That means that every point on this curve has a slope. That's where our next thing happens. That's where our next step, our next logic happens. For nonlinear data, there are many slopes. Unlike linear data, there's one. Okay, coming back to that. For objects speeding up, the slopes, since there are many, the slopes go from 0 to large. That is, the velocity goes from 0 velocity to large velocity. And a picture of that from our velocity time graph here, going from 0 to large. And as stipulated in this example, it's in the east, so therefore it's in the positive y-axis. So we go from 0 to very large velocity. Why? Because the slopes here are 0. Right here, basically, it's nothing. From 0 to very large. The slopes increase. The slopes are getting larger. Therefore, the velocities are getting larger. So yeah, let's take this, let's dissect this and next. So our motion map accordingly will be small gap here or whatever gap, and then it gets larger and larger and larger to denote that the object is accelerating. Oops. That is, object is speeding up. Object speeds up. So again, just to repeat, our claim was, at least from the homework, car speeding up, increasing position in the east only. Or another example, I have a car speeding up, increasing position. I didn't have a direction, so you had the choice to whatever. Okay, that's my claim, and then I have some arbitrary data that goes from 0 to positive 200 because I'm in the east, so I know that I'm going to be positive numbers. So I just arbitrarily choose these numbers: 0, 0, 5, first, second, 18. I start growing, getting dramatically larger, and the gaps are increasing. I can go further and further until I stop at 200 or near 200, get to 188, stop there, whatever. But that's my data, that's my evidence. Now I take this data, I know it's nonlinear, gaps are increasing, and I plot my points, curve. I also know by definition that the slopes, plural, there are many slopes. Those slopes are going to grow from 0 to large. And we'll draw this again just for effect. But the slopes tell you what the velocities are going to do because that's the definition. The slopes tell you what the velocity is doing. The slopes are getting bigger, the velocity is getting bigger. If the slopes are getting smaller, the velocity is getting smaller. I mean, if we had a line like this, I'll erase it. The slopes are getting smaller. We're slowing down. That makes sense. Okay, so it's all about the definitions. You apply it. We need to have this in our toolkit before we go to the next part of our project down the pipe. You have to really know this. Okay, and you have your notes so you can refer back. Motion map, and then I had the quiz. Yeah, if you haven't already, check out this other YouTube channel, The Science Asylum. The guy is really cool. So yeah. All right, then we went here. Okay. So let's just do that curve for effect, right? So we had our data. Let's say that I'm not going to repeat all that stuff. So, see, the reason my lines aren't straight, I'm sitting down, but my computer, better if I was at the whiteboard, but anyway. So let me try and get this as straight as I can. Okay. Okay, so position, I'm not even put the numbers in, I'm just gonna do a curve. Sophia Lorenzo, is my object speeding up or slowing down? I'm looking at this graph, what could you tell me? Tell me privately. Rita, what's happening to my object? Yes, Sophia. I'm sorry?
Yeah, I was gonna say it's speeding up.
Yeah, you both right. Speeding up, accelerating. So what do the slopes tell me? Monte, what do the slopes, are there many slopes or one slope?
One slope?
Bro, many slopes. Velocities are increasing, Lala, yes. There are many slopes on this guy because of curve nature. And okay, let me see if I can get a little bit more empirical than that, because I don't like to be arbitrary. And arbitrary is not gonna work for you. All right. Let's get some gaps going. There are many slopes because each point here is going to have a line associated with it that's going to look different than each of the points, all of the other points. Now, of course, this is near infinite number of points. We can choose 4. Let's wait. That was supposed to be red. Okay. Okay. Now, in order to kind of visually see this, this is where it kind of maybe gets a little bit misty, airy. Can't really touch it, but these slopes are different because when we draw something called a line or a tangent line, a line that touches each point, you're going to see that the slopes of all of those lines, the slopes of each of those lines is going to grow. It's going to get steeper and steeper and steeper, as we saw in the other example. So why don't you do that right now? Just do your best. Now, when you draw this tangent line, okay, you want to make sure that the line touches in the middle, and then it goes to the x-axis here, and then do your best to have the top part come off of the curve. That wasn't very good line, but you want to make sure that it kind of comes off and then it touches the x-axis. Do your best for the rest of the points. Come here, and then something like that. Even if you have to kind of fudge, but that's what, the effect should be, kind of coming off the curve at the top and touching the x-axis at the bottom. Just visually, just looking at all these points, you can see that the slopes, if you were to take the slopes, that they're getting larger and larger. So this wasn't the best, but we saw it before on the other picture. Let's say here, this is slope 1. Slope 2. Because for each point it has a slope. Slope 3. 4. You know that the slopes are getting larger. They're increasing. The object's speeding up. The gaps are unequal. There's a lot you can say about it. Since the slopes are increasing, what's happening to the velocities? And we have an answer.
Since the slopes are increasing, wouldn't the velocity also be increasing?
Yes, absolutely. Slopes are increasing, velocities are increasing. Those are the definition, that's the relationship. So slopes are very important. We are actively applying what we know about slopes from the algebra classes into physics. That's how we do. Slopes are increasing, therefore. The velocities. Yay. And that's in the east, positive y-axis. So let's draw a line that describes this. And it's going to be a line because these are tangent lines. These are slopes of these are velocities that are going to grow. So in order to show that properly, we must draw a line in velocity time to show that the velocities are growing. So we go from curve in xt to line in vt. Units of velocity, meters per second. We go from 0 to large in the east. And if it was west, and then this curve would be a certain other direction, it would actually be If it was west and growing, increasing position, we would, well, we'd have a curve that in xt, the xt curve would look something like that, because then the velocities would get larger and larger in the west. And that's for later. Okay, so would the distance from 0 to the first point be the velocity for 1 second? Yes, that would be correct. So Arthur asks, would the velocity here be for 1 second? Yes, it's the velocity at second 1, 2, 3, 4, and 5 if I had a fifth. Yes. All of these velocities are velocities at each point. So therefore, to Arthur's question, let's say that this is 1, 2, 3, 4, let's say 5 if I had it going. The velocity here, let's say that that's 2, making up a number. Obviously, this is going to be larger because it's getting larger in velocity in the east. Let's say 5, just exactly, the same division, something like that. So each second, there's a different velocity because each second there's a different slope, right? Each second the slopes are getting larger, yeah. And then, so this line goes here like that. We go from curve to line in velocity, then acceleration. So then now we're looking at a VT graph, and then we can then say the slope of a velocity time graph is the acceleration. I abbreviated that. So now we look at this. How many slopes are here? One or many?
One.
Only one slope. Let's take that slope. Is that slope going to be constant? Is it the same slope for all points? Let's see what we got here. 2 no answers. Incorrect. The slope will be the same. Because if I take the slope from up top here to down there, it'll be the same as the slope between these 2 points. The slope of a line is just a constant value. No matter what points you take. Go back to your previous definition, the previous notes. The slope here will be the same for all points, or any 2 points. All right, so then now we can go to the acceleration time. And knowing that the units of acceleration meters per second squared, the slope of a velocity time graph is the acceleration. That slope is constant. Therefore, it's only one slope. So the line in acceleration time would just be a straight line to infinity. Because it's constant. It doesn't change. The slope here doesn't change. We keep reminding ourselves of that relationship. So when we have a line like this, we see this, there's only one slope. And it's constant. Just saw that in the previous slide, but always remind yourself. Any questions on that? So this is why our motion equations that we're about to see will be based on the fact that acceleration must be constant. How is it constant slope if the numbers are different? Because it's proportional. Like 6/8 and 3/4 is the same value, right? 0.75. When you take the slopes here, that's going to be the same as between here and there, or here and there. It's all a proportion. Even though the numbers are different, they come out to the same value. 6/8 to 3/4 to 12/16, so on. Those all give you the same value, even though the numbers are different, obviously. You understand? Or any other additional questions? Okay. Just prove it to yourself, though. Also, meaning, let's see, I go back here. The slope between 10 minus 5 over 2 is the same as 20 minus 5 over 3. That's 5, isn't it? That's why it's the same. And on an intuitive levels, the gaps are the same. So you're never going to get anything different. Okay. So again, this is same value, 2, 3, 4, 5, or whatever. Okay, so now let's go back to our motion worksheet. I think we're ready to fill this in. Start filling in the velocity and the acceleration. We basically did that already. Let's do that together, right? So we already seen this. I just showed it there. This curve has increasing slopes, therefore my velocities are increasing. The slope here is constant, therefore I have a constant acceleration. Anything strange or awkward about that? Questions? Now, here's what I need you to do now. What's happening to the object in number 2 here? Speeding up or slowing down?
Slowing down.
It is slowing down. And then let's see. Yeah, Daniel, thank you. Why is it slowing down? What's happening to the slopes?
It's getting smaller.
The
I don't
slope, yeah. The slopes are getting smaller this time because we started at a large slope here. Let me just go back to another picture. Okay, and then, so we have this curve right here. Time. Whatever. And so now if we were to draw these lines, you don't have to, you can just kind of eyeball that graph as you did, you'll see, oh, I'm gonna draw it on the outside of the curve here. This time we're gonna have the tangent lines fly off, but then, you know, hit the y-axis here. You don't have to have them hit the y-axis, but, you know, I do that for effect. And then, oh, let me try and do this on the close. If we were just looking at these red lines, from this line here, the slope is steeper than the rest. You can see that the slopes start to get smaller and smaller until they get perfectly straight. If you get the slope will be perfectly straight at the top of this curve. And if that line is perfectly straight, there is no slope at the top. There's no rise, just run, right? So therefore, at the top of this curve, there will be no slope, meaning no speed. So you can see that those slopes are getting smaller and smaller here. So in a curve like this is slowing down because the slopes are getting smaller. They're going from large slope to zero slope, AKA large velocity to zero velocity. We are getting slower. So now, see me finish this up here. Slowing down. See what I'm going to say. Slopes are getting smaller. One last thing. Let's see. They're going from large to zero. Therefore, the velocities are going large to zero. Okay, quick question. Yes, yes. Of course. Large slope to zero slope, yeah. Velocities are large to zero velocity. And since the slopes are doing that, the velocities are doing that, that proves to you that the object is slowing down. From large to zero slope. Yep. Okay, so why don't you fill this in now? What's going to happen to the velocity time curve? Where does it start? Where does it end?
Do you want us to tell you or just?
Yes, yes, yes. Go ahead.
Oh, it's going to start off large and then go down. So the opposite of the first one, but not crossing the x-axis.
Not crossing the x-axis because we're stopping at zero. Because at the very top here, if you can see this pointer, this is zero. So we're not going to cross the x-axis yet. Is the velocity time graph always a diagonal line? Nope. There's no always, unless you're talking about constants. Yes, we're going to stay away from absolutes, but as much as we can, because it just doesn't dictate that. All right, so we're going to start from large to zero. Is it always the diagonal line? I'm not going to go ahead and say that. We have to, in physics, we have to do what's there. We have to take what's given. And that's based on the concepts, understanding concepts thoroughly, which is through time. I'm not doing it as an admonishment type of thing. I'm just saying, because I know we have a tendency to want to think that it's always going to be a certain way. Nope. What always is there is the understanding, the concept. And then we manipulate based on the concept. So that right there is where you come in. You have to practice, you have to work it, you have to be diligent. Okay, so now this is, okay, here's one other thing to note over here. This is a constant slope, yes, but what else can we say about this slope? We just said it here. This is constant and what else type of slope? Constant. Starts with a P.
Positive?
Yes, it's a constant and positive velocity, constant positive slope, constant and positive velocity. Why? Because we're in a positive domain for one thing. Well, actually, that's not the reason. It's just that this is the nature of the slope. It's positive. It's increasing in value. So it's constant and positive velocity. So therefore, actually, no. My bad on that. Constant and positive slope. Because obviously this is not constant and positive velocity, it's increasing. So the slope here will be constant and positive slope. Therefore, this will be constant and positive acceleration because the definition of velocity times acceleration is the slope of a velocity time graph is the acceleration. Therefore, since the slope in VT here is constant and positive slope, therefore acceleration is constant and positive acceleration. Because the definition, constant and positive acceleration. What about this slope? What can we say about this slope? Is it constant?
Yes.
Yes, and it is negative. It is totally negative slope. Because this value down here, if we were to take the, let's say this is 15 up top, 0 minus 15 is going to give you a negative value divided by whatever time interval, 5, whatever, cares. The numerator, okay, it's going to be negative. It's going to be a constant and negative slope, leading to a constant and negative acceleration. Constant and negative. Make sure you understand this. Look at it. Work it. Come one. Okay. Ask questions. Yes, it's constant because it's a line. That's one thing we understand, that the slope will always be one value. When we have a line, it's constant and only one. But what kind of constant slope do we have? It's negative, constant and negative. Therefore, we have a constant and negative acceleration. And question, comments? Let's see. How is acceleration constant if it slows down? The speed is slowing down at a constant rate of acceleration. It's not the acceleration that's slowing down, the speed, the velocity is slowing down. Okay, when you put your foot on the brake, you usually have your foot, let's visualize it. When you have your foot on the brake, you usually don't pump it. You just put your foot down and you notice that your speedometer slows down, AKA your velocity. So it's not the acceleration slowing down, it's your velocity slowing down. Don't get that confused. All right, now what I would like you to do here is to fill in these blanks yourself. And let's talk about it. Maybe we go to breakout. Any questions beforehand? So I'll give you the breakout. We'll come back. Let's go breakout for like 10 minutes and talk about it. Does that make sense, Arthur? Are you understanding that? Okay, but it is a very good question. It's common, I understand, because when we want to think, because when we see the word like say decelerate, it's like, oh, the acceleration is slowing down. No, it's just the acceleration is going in a different direction. Velocity is coming to a stop at a constant rate 2, -2, -9.8 for gravity. So, and this is, so let's just talk about the descriptions here. Right, so I can put my foot on the gas, I speed up. Put my foot on the brakes, I slow down. Let's go to breakout for like 10 minutes and we'll come back and talk about the relationship of acceleration and velocity. Okay. So, do I have the, all right, I'm not gonna do that assignment, take too much time. We need 4 breakout rooms. Let's see if we guys can talk amongst ourselves, get this answer, because this is very crucial for the next part of our project. 10 minutes. Okay, here. Here we go. See ya. Right. So the line here is, thanks for coming back. It's going to be have 0 slope. Right, because if we, like when we go back here and we took the slope of the velocity time, the slope of a velocity time is acceleration. There is no way we can take a slope here. There's 0. That's a 0. That's none. That's nothing. So there's nothing after acceleration, at least in our context. And there's no slope here. When you have a straight line, there's no slope. Nope. So here, our slopes are going to go from 0, or they're going to go from large to 0. So large, 0. So all we're doing here is we're looking at this. This is the left-hand side of that graph. We're going from large to 0 slope. Therefore, our velocity will be, if we were to track it, let's say that this is the same time interval. You don't have to do this, but just for visual purposes. At this second, we're going to have a particular velocity, a particular acceleration, and a particular position. Position, velocity, acceleration. So we know from large slope to 0 slope, which means we're going from large velocity to 0 velocity, right at this point in time. And then what about the slopes up top here? Let's get to Alex. What's happening to the slopes here? From, I'll give you a hint. This is going to go from 0 to what? Maybe I'll just spread the joy around. Mark, what do you think about that? So now we're at 0, but we have to continue because we have this leg here. Anybody else want to help out with that?
It's going to go back up for the velocity.
Okay, so let's dissect this even. This is one we haven't seen, but you know, there's going to be things that we don't see. We have to infer based on what we already know. So here at the top, there's no slope, therefore there's no velocity at this point. And And what do you think is happening to the slopes of each of these points? Are they getting larger or are they getting smaller? If we were to draw the lines,
They're getting larger.
they're actually increasing. But what kind of slopes are they? They're going to be positive or negative slopes?
Negative.
They're going to be negative slopes. Let's draw a couple of these lines just for clarity. Tangent line here, and then we have another tangent line here. Both of these lines have the same picture as this line here. This is a constant negative slope of this line. These lines are like this line up top. There's multiple ones. There's more than one slope. But all of these slopes are constant and negative. No matter how many there are, they will be constant and negative. So therefore, on this leg of the trip, the velocities will be constant and negative. And they're getting larger and larger. So here we have negative slopes that are getting larger and larger. And since they're negative, we're going to be in the west domain. So these are all the negative positions. This is the positive positions. And back up top here, even though these slopes were going from large to small, they were all positive slopes. So that's why we stayed in the positive domain until we got to 0. Then here, the slopes are getting larger, but negative. Larger, but in the negative velocity. So say that if this is -1, let's say this is -10. They're going from 0 to very large in the negative direction. East, west. So this is what the graph would look like for the velocity time with respect to this position time curve. A little bit tricky, a little bit combination, but we will have several practices on that so that we can get that. So now what about this line? Is it going to be one slope or many? It's just one big line. How many slopes do we have here? One slope or many slopes?
On the velocity time graph, we have one slope.
Okay, for this particular type, whether it's velocity time or acceleration time or position time, when we are looking at a line like this, the slope will always just be one slope. And likewise here for this line, there's always one slope. It's constant and negative, but it's always one. So even though this line continues through the negative domain, it's all one line. How many slopes does this one line have? I just told you.
1.
It's going to be one negative slope that continues on until we stop it. But it's one negative slope. Yep. So then what kind of slope is it? Is it positive or is it a negative slope?
It would be negative, right?
It would be a negative slope. Do not ever be confused that it crosses the x-axis and now things get murky. It's all one line, ladies and gentlemen. Nothing changes conceptually. Visually, sure, but nothing changes conceptually when we're just looking at a line like this. The slope is always one, whether I stop here, I continue on, I go into another axis. As long as it's one line that looks like this or looks like this, we have one slope. And in this case, it's one positive slope, hence we have the positive acceleration. And here we have one negative slope, as we have a negative acceleration. So nothing changes conceptually. With practice and time, we should get comfortable with that. Okay, so negative slope, one negative slope, that means I have one negative acceleration. It looks like this. One constant negative acceleration. Any takers on this one here? Did anybody do this? Oh, well, we will stop here for the day. We are very full. And I would, let's see, why don't I'll make a slot for this motion in a straight line. I want you to turn this in. And I will be assigning some work over the weekend for next Tuesday. We had a last question. And don't worry, as we will do this again to make sure that we understand it completely. Okay. If there's, because this is new, but yeah. So yeah, let me make the slot for this, and you can turn this in. Okay, I think that's gonna do it.